So this next example is going to show off a bunch of STL non-mutating algorithms that check for the max and the min elements in an iterator range. And we'll see that there's a couple different variants we're going to look at. One is called max element that finds the largest item in a range, and you can use a binary predicate if you want. Then there's also min element, which finds the smallest item in a range. You may also use a binary predicate. And much like find and find if, you get an iterator back to the max or the min element found, which should always be found. It should always come back with something unless the range is empty. So if the range is empty, then you may come back with nothing, but otherwise you should get a max or min iterator. Now, one of the things that's really wonky about this is that they don't actually have, even though there's a version of this that takes a predicate, they don't have max element if or min element if. They're all called max element and min element. And I think that that's in there just for backward compatibility purposes. I've never understood why they omitted the if, because everything else is pretty consistent in that respect. You'll notice that max element and min element require forward iterators, not just input iterators, because they have to save the iterator of the largest and or the smallest element found. And an input iterators doesn't support saving. You can't assign. You'll also see that by default we have max element and min element using operator less than, or you can pass in the predicate. As I mentioned before, that I don't know why they don't call it max element if and min element if for the predicate version. So we're going to look at a couple of different examples here. We're going to have a functor that I'm going to use called max odd. And when we need that, I'm going to come back and show you what max odd does. Right now, what it's going to do is it's going to check to see whether a number is odd, and if it is, whether it's greater than the current max. So keep that in the back of your head. We'll come back and re-examine this in a minute. So also to make this example interesting, I decided to show you off yet another STL container type or pseudo quasi-container type. And this is something called an array. And an array is basically just a very, very thin wrapper around a built-in array. So it's pretty much like a built-in array, except as you can see here, what it does is it defines a statically defined array in its data member, its private data member portion, which is given the size that's passed in as the second parameter to the array class itself or array struct itself. So array is parameterized by a type, like an array of int, and it's also parameterized by a size. So you can see this is just a very, very thin wrapper around a built-in array. And then there are various operations here like fill n and swap. And then the other thing that's cool here, and the reason I'm doing this really is to show you how we're able to use operations like begin and end and so on the underlying array, because it's able to know things like how big is the array, because it knows how big it is because it's passed in as a parameter. So this is nice. It gives you an array-like mechanism that has pretty much exactly the same space overhead and runtime overhead as a raw array, an int array, but it wraps it up in a way that makes it work more like a typical sequential container. So we're going to make an array of 9 elements, and we give those 9 elements here in the initializer list. And then we go ahead and we look for the max element. So this is going to give us back an iterator that'll tell us what the max is, and I think the max is probably going to be 67. And then we go ahead and find the min element, which I think is going to come back, and the min element's going to be something like, maybe minus 40. And then we're going to go ahead and do some wonky, crazy stuff here. So we're going to go look for max element, except we're going to look for the max odd element. And so if you look up here, max odd takes 2 parameters. It takes the current max. So there's a running count kept of the current max by the max element method. It's the predicate version. And then there's the current element that we're looking at. And so the current element in the range that we're looking at, we check to see if it's an odd number. And if it is an odd number and it's greater than the current max, which is held internally by this max element method, then we return true. And then internally, the max element method or algorithm will update its internal state. So let's go ahead and take a look and see if we can what max element does. So here's what max element does. If the first and the last aren't equal, then we go ahead and we stash the first iterator to a local variable called underscore underscore I, which is a forward iterator. So we have to have the ability to assign one iterator to another. So that's why it's a forward iterator. And then we start at that location at the beginning. And while we haven't reached the end, we call this comp method, which in our case was the max odd method. And we pass in the element that is the element that we're going to be comparing for, and then X. And whenever we get a match, then we're going to go ahead and switch first to the place where the match occurs. So wherever we come back with true, that becomes the new max element. And when we're done, we return the max element, which whatever that was. So this will always return a value, but there's a couple subtleties here, and we'll talk about subtleties after I explain the rest of the example, because it surprised me when I first ran it. The next thing that we're going to do here is we're then going to call min element, except rather than passing in max odd, we're going to pass in a lambda, a generic lambda function. And this is going to take X, which is the element that we're iterating through, and the current min, and if X mod 2 equal 1, if this is an odd number and it's less than the current min, then we're going to return true. So let's go ahead and take a look at min element. And you can see that min element does more or less what max element did. Let's see if we can find max. Max maybe somewhere else we can't find right off the top of our head. But you can see that min element is going to go ahead and go through that range, and it's going to do the comparison, except this time it swaps the order. It does the one that is the current min second, and the element that we're going through one at a time, that one's going to be the first. So that kind of swaps the order, max and min. So let's go ahead and run the code, and I'll show you the results. So as you can see here, it says we found the max is 67 in an array of size. We have 9 elements, that works. We found min, which is minus 40. If you look up here, you can see that is indeed the min. And then we went and we found the max odd, which was 67. And we found the min odd, which came back as 9. And if you look here, you'll see that indeed 9 is the min odd. But here's the part that's funky. If I change 9 to, say, 10, let's see what happens when we run that. So now you can see what comes back. We come back with min odd equal 10. Well, what the heck is going on there? Obviously, 10 is not an odd number, at least not last time I checked. So how is that ending up being true? Well, it all comes down to what the min element method is actually doing under the hood. So if you go over here and look at min element, you can see it starts by stashing the first iterator here. And then, so first is going to keep set to whatever the first element was, and then we iterate through I, or underscore underscore I. Now, if we never end up getting a match, first still points to the first element in the vector, or in the range. And so as a result, that's always going to get returned. So something always gets returned, except if the first element turns out not to be odd, then you're going to get a very strange result. So I guess the lesson from all this stuff is that this has some unexpected behaviors, and the expectation here is you're really just probably really just want to do a comparison of X greater than current max, as opposed to this odd, funky odd thing, because you get unexpected results. At any rate, I thought you might get a kick out of seeing max element and min element, because it's a somewhat different kind of algorithm than some of the other ones that we've looked at before. There's no predicate version, there's no underscore if. There is a predicate parameter, but there's no max element if, min element if. And you have to be careful with what you pass in as the predicate, because it may have some unexpected behaviors.